Okay, so uh, okay. So what did we learn? Uh, we learned about the Carnot. So the previous class, right? So why do we use Carnot? So in order to optimize Boolean equation graphically. So it's this. So as I mentioned, we can optimize Boolean equations using several axioms and then theorems. Okay, but so sometimes it's not figure out how to optimize. Many students. So sometimes it's not easy to figure out how to optimize the Boolean equation. So we can use kernel map, and then actually if we use the kernel map, then we can easily figure out which factor or which terms can be optimized in the Boolean equation, right? So we can, as I mentioned, we actually kernel map exploit the kernel map utilize the combining theorem, right? So if we apply combining theorem, then we can remove one of the terms in the Boolean equation, right? So and then and when you apply a kernel map for optimizing the Boolean equations, then you need to know that actually the order of this these input need to be 0, 0, 0, 1, 1, 1, and 1, 0, right? So you need to know the order of these input values. And then, okay, so, and then also you need to know some rules for applying kernel map, okay? So this is very important. And then I mentioned that this is also important actually. So we need to represent kernel map on the paper, right? So it's a 2D paper. It's a 2D dimension, but actually the kernel map is the edge of kernel map. Okay, this edge is connected to this edge, and also, so this is the actually two line. So, but if there are four rows, then this edge is connected to this edge. There are four. If there are four rows, okay. So you need to know. You need to remember that a circle may wrap around the edges. Okay, so this is very important. Sometimes we may forget wrapping some on the elements in the edges. Okay, so and then also if a truth table includes the don't care output, then it means that the output can be 1 or 0. Okay, so any outputs, any values are allowed. Okay, so and then actually this is very good for optimizing Boolean equations, right? So if we do not if we do not specify any specific values for the some output of Boolean equations, then we can apply the optimization further. Okay, so the good thing is that the x can be included in the circle, or x can be excluded from the circle, because the x can be 0 or x can be 1. So if we can apply some more optimization, then we can think that x is the 1, okay? Then we can make the larger circle. So I also mentioned that in the kernel map, it's very important to make larger circle, okay? So the largest circle as possible, okay? Okay, so kernel map. So now we will move to the different topic. It's a hardware description languages. Actually, so in this course, this is very important topic. So we will learn we will learn about the syntaxes and then how to use audio description languages. Okay, it's very similar to the programming languages, right? So why do you use programming languages? So if we want to build certain applications, then we need to write a code using programming languages such as C, C++, Java, or Python, right? So actually, so inside of our computer systems, then the computer systems run the okay. Actually, computer systems can only understand the 0 and 1, right? That's what I explained in the previous classes, right? So computer systems are kind of digital systems. And then actually, a computer system can only understand digital values, digital data, or digital signals, right? But if we just use digital values or digital data for building our applications, it may be very complex, right? And then we cannot easily understand the generated code, right? So actually the digital values or digital data are very different from our normal symbols or normal data or normal languages, right? So firstly, we write a code using high-level programming languages, okay? So like C or C++. So in order to write a code, also you need to understand the syntaxes and then some rules of programming languages, right? But it's easier. It's easier than use the digital signals or digital values directly for building for building applications, right? So actually, the very early computer system, actually people built some their built up some punch card. So it's actually each element of the punch card that represent certain digital values, right? And then actually they directly uh, generate some punch card, and the punch card is given to a computer system, and then computer system just execute some instructions, right? But it's very difficult, and then so actually it's very difficult to build very complex applications. So that's why we use programming languages, okay? And then hardware. So the problem is that our computer system, also our digital system, the model digital systems are very complex. Okay, so as you can see, so this is the die photo of Intel Xeon processor, right? I think so. But you know, so this processor includes billions of transistors, and then actually we learned that so basic gate. The basic gate includes, like the NAND gate includes 4 transistors, and NOR gate includes 4 transistors, and the inverter includes 2 transistors, and then also AND gate includes 6 transistors. So 6 versus billions. So how many gates are required for building this CPU chip, this CPU chip? So billions of basic gates are required. Okay, so think about this. It's not possible. It's not possible to build these complex systems using only basic logic gate. So actually, these this this circuit or this system includes basic logic gates, right? But we cannot build these complex systems using basic logic gates manually, right? it's very, very complex and it's very difficult. It's not possible actually. So we can use programming languages like the computer programming languages. Okay, so we can use programming language for building digital system, building a digital system. Okay. Okay, so this is the Intel Xeon, so the die area, and then also we can find the number of transistors. So it's very complex. Then, so think about this. So if we just, so we learned about the basic logic gate, and then we also learned about the Boolean equation, and then we learned that Boolean equations can be built using basic logic gates, but it's very, very, so actually the modern digital systems are very, very complex. So it's not easy. So it's not possible to build these entire systems using the Boolean equation or basic logic gates. Then how can we make the very complex digital systems like a chip? Okay, so this is the BLSI design flow. So BLSI represent the very large what is this? BLSI. Oh, I forgot. Okay, this is the chip. Okay. Okay, so this is the chip design flow. So I say modern chip design flow. Okay. So firstly, we need to specify the target system. So it means that we need to specify the purpose of the systems, or so we can also define the input and output signals, and then also the internal functions of the target system. So this is a very high level design, right? And then we can do the architectural design. Then if the purpose of a target, if the target system, the specification of the target system is decided, then we can design the architectures of this target system. Okay. So architecture means that, so actually in the first class I showed some modules and then blocks, and then these modules are hierarchically organized inside of the larger module, right? So in the digital design concept, I also explained about the three whys. So what are the three whys? Hierarchy, modularity, and what are three I's? The hierarchy, hierarchical design, and modular design, and then what's that? The last Y. Okay, good. We can apply some digital design concepts for building the architectural design, right? And then, so which means that we can define a certain module, and then actually these modules are regularly, right? So a regular module can be included in this large module hierarchically, and then we can build some large module like this. So which means that we can organize a smaller module, and then we can connect the input and output of these modules, right? Then we need to design this small module. Okay, and then this design is called the functional design or logic design. So actually, so that's why we are, so actually the course includes this part. So logic design or functional design. Okay, so we can define the function, okay, or we can define the logic inside of a module, right? And then if this module is designed, then circuit is generated. So actually, so we need to build a digital circuit, a digital system using transistors, so CMOS transistors, right? So which means that actually in order to run the digital system, why not to implement a digital system, then we need to also implement circuits using most transistors. So actually, so we learned that the NAND gate, so this is the NAND gate. So NAND gate can be implemented using the MOS transistors, right? PMOS transistors and the NMOS transistors. So which means that our logic gates are translated into the circuit level design. So this is the circuit design. So it means, so firstly, we design the logic level. So we create the logic level design, the module, and then this design is translated into the most transistor circuits. Okay. So then we need to make the, based on the these most circuits, then we need to make this large chip. Okay. Then how? So this process is called physical design. Okay. So physical design includes this process actually. So it can be a little bit tricky. So, but actually the physical design includes the partitioning, floor planning, placement, clock synthesis, blah blah blah. And then actually these processes are required for building working circuit, working large systems, right? Because actually, in order to build a real chip, then we need to place our module. Also, we need to connect our module. But this module need to be physically verified. Okay, so which means that we need to also make decide. We need to also make some timing closure. So which means that the time specification need to be specified for the correct working. So actually, these processes are required. This is the chip design processes. So actually, so this course will not cover these processes, but this is just some common knowledge. So it's a common sense. Okay, so actually, if you are interested in hardware, then so this is kind of some common knowledge. Okay, then the physical design needs to be verified. Okay, so it needs to be verified. So which means that so as I mentioned, the timing was some power consumption need to be simulated and then verified. Okay, and then the fabrication. So real design. So, so I believe some students have heard about the fab, okay? It's a semiconductor fab such as the TSMC or Samsung, okay? Actually, so from this, we just make some schematics. So this is kind of design schematic. In Korean, it's called 설계도, design 설계도. And then actually, this is schematic. Okay. So actually, some companies, and was some vendors, and then IC vendors was some VLSI vendors just to make the schematic. Okay. This is, and then, but the real chip or real physical chips need to be manufactured by fab. Okay, and then this process is called the fabrication. Okay, so this is kind of real physical manufacturing, like by TSMC or Samsung. Okay, so those companies include the fab. Okay, it's called fab. It's a factory for chip. Okay, and then they really make the chip physically. Okay. So, and then this process is called the fabrication, and then we can just include some, add some packaging, and then we can make the final product, it's a chip. So actually the various design includes the many steps. So that's why the various design is tricky, and then it includes the very high level technology and then very high level engineering skills. Okay. So that's why the semiconductor industry is very critical, and then it's a high level technology, right? So this is the chip manufacturing process. So then why do we need the hardware description language? So actually we need the hardware description language before this level. Okay, so functional design or logical design. Okay, actually, as I mentioned, the modern chips or modern digital systems are very complex, and then it's not possible. It's not possible to build these complex systems using by organizing basic gates manually. It's not possible. Okay, so we need to use programming languages. Okay, as I mentioned, in the first first part of this class. So why do we use programming languages? Because we want make code easily. We want to make code using our familiar interfaces like languages, okay, like the high level languages such as English, right? So that so and then this code is translated. This code is translated to the instructions and digital data that can be understood by a computer system, right? And that's the same. We use programming language, and then this language is called a hardware description language. Then it's called HDL, hardware description language. Okay, it's very similar to the programming languages, but we use hardware description languages for building hardware systems. So target is different. So why do we use programming languages? Because we want to make applications, right? But applications include digital data or instructions that can be understood by computer. Okay. Then why do you use hardware description languages? Because we want to build a hardware system. Okay. So this is the purpose of the hardware description languages. Okay. So HDL, the hardware description language, or HDL, so this describes the structure and behavior of electric circuit. So I will explain later about the structure and behavioral design, but so you need to understand that HDL, using HDLs, we can describe structure. So structure means that the modules are organized, and behavior. So behavior means a certain Boolean equation behavior or some higher level behavior of circuit can be described. So it's the same for the programming languages, right? So using a programming languages such as C or C++, we can describe the structure, right? The function or class or structure. So we can define functions, classes, and the structures in C++, right? And then we can organize these structures to build larger programs, right? Also, we can define behavior of our program, like the C equal A plus B, D equal C plus E, something like that. So it's the same. We can, using our hardware description languages, is we can describe the structure of hardware and the behavior of hardware. But you need to remember that the purpose is different, right? So why do we use hardware description languages? So because we want to build real hardware. Okay, we want to build real circuit. Okay, so I mentioned that in this step, the functional design and logical design step, we can use hardware description languages for building a certain system, right? And then this is translated into the circuit design. So the purpose of hardware description language is to build a circuit target circuit design, right? So this is the purpose. So actually, if we just actually this is very important. So if we write a code using HDLs, then our code needs to be synthesized. So in Korean it's called 합성, right? Synthesized into circuits. Okay. So why? So it is important because some students think that this is kind of a program language. So actually, so when we use a program languages, then we can run the compiled code, and then if the result is okay, then we can say that, oh, our code worked correctly, and then it's done, right? So in a software design, if a code generates the correct output, then it's okay. Okay? But the hardware design, so the purpose is different. So it means that the in the hardware design, so actually the the code by the HDL needs to be synthesized into the real hardware. So it means that even though our code generates some correct value, but after synthesis, then our code may be synthesized into incorrect hardware. Sometimes if we just generate the code incorrectly, if we just write the hardware description language code incorrectly, so even though the simulation result, like the software result is correct, but the synthesized result may be incorrect. Okay, so you need to remember this. Okay, you need to understand this. Okay, so as I mentioned, software, if the result is correct, then it's okay. But the hardware, even though the result is correct, the synthesized hardware may be incorrect. Okay, and then actually we need to focus on the synthesized result. Okay, because this is the purpose of hardware description languages. Okay. So this is the summary of the hardware description language. So definition. HDL specifies logic functions, okay, like the Boolean equation and the Boolean logics. And then describes behavior and or structural models of digital circuit. So this is actually the same to the programming languages, other programming languages. So as I mentioned, we can define the behavioral or structural model of the software. How the description language describes the behavioral and or structural models of digital circuits, so hardware. Okay, and then we can use the computer aided design. It's called the CAD tool. Okay, computer aided design tool to produce or synthesize. Okay, you can find the terminology synthesize, the optimized gate. So this is the kind of digital circuit. Okay. And then, so actually for the most hardware design, so we use HDLs. Okay, actually. Okay, so in the real world, in the industry or academic community, that we use the two leading HDLs, like the system verilog and then VHDL. Okay, so it means that there are two very popular HDLs. Okay, so system verilog. So actually, just the industry widely used the system verilog. Okay, and then actually, so actually in this course we will also learn about the system verilog, and then it is because the syntax of the system verilog is similar to the syntax of C. Okay. So it is developed on 1984, and then actually this is the IEEE standard. Okay, so it's a standard design hardware description language. Okay, and then it extended in 2005 because it started from the Verilog. Okay, Verilog was developed in 1984, and then it is extended, and then the system Verilog is the optimized and then more enhanced version of Verilog. Okay, so system Verilog was firstly designed in 2002. So its extended standard includes the system Verilog. Okay, so we will learn about the system Verilog. Okay, and then VHDL. The VHDL is another hardware description language, and then it is developed in 1981. So earlier than Verilog. So developed by Department of Defense 미국에서 in the U.S. United States. Okay, so this is VHDL is also included in the IEEE standard. Okay, so standard audio description language. Okay, but the VHDL is so syntax of the VHDL is more complex than Verilog. So if you are interested, that you can learn. But in this course, we will learn about the syntax of system Verilog. Okay, so and then also there are other the hardware description languages such as system C. Okay, so it's just actually the system C is the C++ library. C++ libraries for defining the behavioral model of the digital circuit. And then in the academia, so some academia communities have developed CHIZU. So CHIZU was developed by University of California at Berkeley. Then the BlueSpec was developed by MIT. Okay? And then so there are several other hardware description languages. Okay? But these the system Verilog and then HDL are two leading hardware description languages. Okay. Then, so actually we use hardware description languages for simulating our design and synthesizing our design. So what is a simulation? If we simulate something, then it means actually it's not real behavior, it's not real result, right? But we just emulate. So it means that we just run our system in a software manner, right? It's a simulation. And then we can check the output or some internal values, right? So, so simulation is a kind of the execution in a software manner. So, for example, if we can run our programs, right? So if we write a C code, then we can compile our C code, right? Then we can run our C code, right? So then we can check the output of our program. Before, if we do not compile our C code, then we cannot check the output, right? It's a kind of simulation. So we can check the output of our code in a software manner. The hardware description language, it's also programming language. So we can simulate the code generated by hardware description languages. Okay, but it's kind of software manner. Okay, so it's similar to the we can compile the HDL code, and then we can run our HDL code to check the output values and then internal values of our hardware design. And this is called simulation. Okay, we can simulate our hardware description language code. So it is required because output check for correctness. If the current system is very complex, we cannot guarantee the correct behavior, correct execution, right? Actually, every code includes bugs, right? Every code includes bugs and then also wrong implementations, right? And then we need to run our codes, and then we need to fix the some incorrect implementation. Also, we need to catch the bugs, right? It is also required for the hardware design. We can build the hardware using the hardware description languages, but our product always so software code always include bugs or incorrect implementations, right? It's obvious, right? So we need to fix these bugs or the wrong implementations. So we need to simulate our code. Okay. It's in simulation and the debugging in simulation. So billions of dollars can be saved. And synthesis. So this is the translation. So what does that mean? Actually, we can, so with using the HDL, we can describe structure and behavior of our design. But in order to make a real chip and in order to make the real system, then these need to be translated into circuit. It means the basic logic gates, okay, and then transistors. So synthesis represents this translation. It means our code, our HDL code, is translated into some basic logic gates and then transistors. This is called synthesis. Okay. So it's in Korean it's called 합성. Because synthesize represent the 합성. Okay. So these are two main purposes of HDL design. So this is just some comparison. So This slide shows the process of compilation. So how do you, high level language to the machine code, computer system. So we can write the code using high level languages such as C, so like this, and then using a compiler, this high level language code is compiled into the assembly code, and then using an assembler, then this assembly instructions are translated into the digital data, digital values, okay, like this. So this is some comparison of the software code. So how the real software code is translating the digital data. But in the how to describe language, so this is also the example. So this is the system value code. So it's a very simple code. C equal A plus B. Okay, it's just addition, right? But if you see this figure, so you can find that actually this code is translating this schematic. So how can you observe? So you can observe many basic gates here, like these are basic gates. And then you can observe that basic gates are connected each other, right? Actually, from this very simple code, it's an addition code, then this complex schematic, okay? It means that the many basic logic gates are allocated and then organized, and then these basic logic gates are connected each other, okay? So if we write a system value code like this, then after synthesis, this schematic is generated. And then, actually, these basic logic gates can be implemented using transistors, right? So actually, these transistors are mapped to the basic logic gate, and then so connected each other. So we can make very complex circuits. Okay, so you can compare. If we use the programming languages, then this is the final product. Okay, what is the final product? Final product is the digital data or the instructions that can be understood by a computer, right? So this is the high-level language code, but after compilation, then this is generated. So digital data, digital values or digital instructions are generated. But what is the final product of hardware description languages? The final product of hardware description language is the synthesized gate. Okay, like this. So it's a translate, then these gates are generated. So you need to understand this. Actually, the process is very similar, like the compilation, synthesis. It's a kind of translation, but the final product is different. Do you understand? So this is the final product of the HDL. Okay. So this is important. So it's red colored word is important. And using an HDL, think of the hardware. The HDL should produce, generate. Okay. So as I mentioned, the final product of the HDL is the hardware. Okay, not the simulation result. Okay, so it means that we need to generate the correct. We need to generate the correct hardware using hardware description languages. Okay, So this is very important. So here of treating HDL like software because it's not. So it's very similar to the programming languages, but do not treat the HDL code like software. This is very important. Okay. It means it needs to be synthesized. So for this purpose, we need to implement the HDL code correctly. Okay. So for the correct hardware design. Okay. Do not treat HDL like software. This is very important. It's not software. Okay. The final product of the HDL is not software. Okay. Red colored one, important. Okay, so this is the example. So actually, so if you run this, so this is the system value code, right? And then I believe you can estimate the output of this code, right? So it's a hello world, okay? So and then this is the display, and then it's a hello world, and then finish, okay? So actually the output of this code is the hello world, right? Like the hello world C code. Okay, so it's okay. And then there's no error. There are no errors in this code. Okay, so we can compile. We can compile this code without any errors. Okay, and then we can simulate. So which means that we can get result from this code, but it's not sensitizable. Okay. So even though this code generate the if this code display hello world on the screen, but this code does not implement the hardware that display hello world. It's not synthesizable. It's just a software execution and then simulation, but it's not synthesizable. So we can use this code because we can simulate our code, and then we can debug our HDL code. Then we can use this not unsynthesizable representations. But it is required actually for debugging. But you need to remember that this code is not synthesized. So it means that we cannot build the correct hardware using this code. Okay. Okay. So any question? Because actually this is the different types of programming languages, so you may be a little bit confused. Okay. Any question? Okay. Okay. So now, we will learn about the basic syntaxes of system variable. Okay. Firstly, we need to understand the module. Okay. So actually, in the data design concept, we also learned about the module or modularity. And then what is the module? So it's a kind of a black box, and then the input signals are connected given to the target module, and then output values are generated by specified function. So this is kind of a module. So we can describe the module like the black box, like here, the black box, and then the input is given, and then output is generated. And then in the system value, then we can define the two types of modules, like the behavioral module and structural module. So behavioral module just describe the behavior, the functional specification of the module. So for example, C equal A plus B. This is the behavioral representation of the addition, right? It just defines the behavior, like the A is the input and B is A, B is our input, and then we just define C, generate the output C, but C is defined as the A plus B. So this is the behavioral module. Okay, we just describe the functional specification. We just describe the behavior of the module. Then, what's a structural module? So, actually, these small modules are connected each other like this. Then, so this is the hierarchical design, right? Then, in order to make the larger module, we just organize the basic logic gate one smaller module, and then we connect the input and output ports of the modules. Okay, so it just defines the structures of the modules or basic logic gate. Okay, so this is the structural module. Okay, let's see. So, okay, I'll show the later. So this is the structure module. So actually, when we write a system value code, firstly we need to define a module. Okay, like this black box. Okay, so this is the example. So now we are learning about the system value syntax. Okay, so first, so in the system value code, we first define a module, and then a module will start using module. Okay, so this is the system value syntax, right? So, and then it is followed by module name. This is the module name. Okay. So if you see this code, it declare a module, and then the module name is example. Okay, it's a module name, and then you can find some input and output ports A, B, C, Y. So this is the description of the module, module. But so actually, you can, if you see the system value syntax, then you can find that the module is declared, and then module name, and then after that, the input and output ports are listed. Okay, so if you see that this module includes the three inputs A, B, C, and then one output Y. So all input and output ports are listed after the module name. And then the type of the input and output ports are defined after this line. Okay, so you can find, oh, this is the input A, B, C, A, B, C here, and output is Y. So using the module declaration, then we can define this module description. So we just define module name, we define input ports, we define output ports, right? Like here. And then finally, this module will need to be ended with the end module. So this is the pair. So the module needs to be declared using module, okay? And then it need to be and it need to end with the end module. Okay, this is just a pair. And then this is system value syntax, and then module is declared. So see. Then inside of module, so it's another representation. Oh, so and then this slide shows the another representation of the module. Okay, so what is different? So in this representation, then I just declare a module named example, and then the input and ports are just listed, and then the input and ports are described after the input and output ports listed. But it's just we can just define the type of input and output directly inside of this bracket. Okay, so it's a not different type of declaration, but it's the same, right? So using a module syntax, then we can declare this description like a module name, and then input and output ports are defined. Then we need to define functional specification, right? So when we learned about some hardware concept, then the hardware components need to include the input port, the input signals, or output port, output signal, and the functional specification, and then timing specification. So using a hardware description language, we need to describe these factors like input and output ports and functional specification, and if required, timing specification. So now we need to define functional specification using behavioral models. So this is the example. So as you can see, so these are inputs and this is output, right? And then output is defined using system value operators. Okay, so you can find that this line is included assign y equal not tilde a and then tilde b and then tilde c, then some order. Okay, there's nothing like this. So we can use we can describe the behavior of a module using system Verilog operators. And then actually we did not learn about the system Verilog operators, but this is the example. Tilde is the not. Okay, it's a bar. Okay, so tilde a, then what is tilde a? Tilde a is the a bar. It's the not gate, right? The tilde is the operator, but it represents not or bar. And is the and, obviously. Okay. And then this is or. Okay. Then what is the functional description? And then what is the Boolean equations described by this code? What is the Boolean equation? So tilde is not, this is not or bar, and then this is and, this is or. So this is the A, B, C plus A, B, C bar, that's the bar, plus A, B, C. Y equal. So this is the Boolean equation represented by this system value code. Okay, this is because this is not, so this is and, this is or. So this is the Boolean equation. Right? Right? It's correct. So using a system value operators, we can describe a Boolean equation. And this is the behavioral model, the Boolean equation, the behavior of our target Boolean equation or functional specification is described using system value syntaxes, right? This is the behavioral model. Then we can simulate. Okay. So this is the module. Okay, it's A, B, C, and this is Y. So we just define a module here, and then we also define the functional verification using the behavioral model of the system value like this. Then, so this is the Boolean equation. So if the input value changes, then output is also changed by input values, right? So then actually in a real world, so actually in the real hardware, we need to consider time, right? Because by time, the input values can be changed. So this is the simulation. So you can find the A, B, C inputs here, right? And then this is time. So time. So simulation, actually in the simulation, we just change the value of inputs by time, and then we check the output of this module. So this is simulation. So we can check the output using waveforms. So this is called waveform. Okay. So if you see if you can observe that by the time, then the input values are changed like this. Okay, like here, 0 to 1, 0 to 1, 0 1, like this. And you can also observe the output of this module. Okay. So this is the Boolean equation, and then combination logic. The output is just determined by input values. Then this is the example of a simulation. And then synthesized. So as also I mentioned that our HDL design code need to be synthesized to the basic logic gates. So this is the synthesized logic. And then also you can find that, different from the behavioral model, right? So actually, in the previous slide, I mentioned, this is the Boolean equations for this behavior model. But if we see the synthesized basic gate from this model, then you can find that, this synthesized result is a little bit, it looks different. Why? Why? So actually, we synthesize the module using CAD tool. Okay, CAD tools. And then actually these CAD tools are called synthesis tool. Synthesis tools. Okay, and then the leader for synthesis tool is the synopsis design compiler. Okay, but when our design HDL design code is synthesized, these tools also apply optimizations. Okay, so this representation and this code is synthesized into is very large gate, right? But during the synthesis, the result is also optimized. Okay, so this optimization, after the optimization, these logic gates are generated from this behavioral model. Okay. Okay, so this is the example of structural module. So you can find that, oh, in this code, you can find 3 modules, right? Actually, it is possible. So in the same file, we can define multiple modules. Okay, it's okay. So so using a system Verilog, so we can just define modules, and then in the same file, we can define multiple modules. So it's okay. So this is the example. And then, so if we just see that this module is the end3, right? There are 3 inputs and then 1 output, and then this is the behavioral model of the end3, right? So you can understand, right? So this is the AND, this is AND, and then these are 3 inputs. So this is the 3 input AND gate. How about the inverter? So this is the inverter, right? So 1 input and 1 output, Y equal tilde A. So this is the bar A. So this is the actually inverter, right? So it's A, B, C, and then this is Y, and this is A, this is Y, inverter. And then let's see the NAND tree. So as you can expect, then this is the 3-input NAND gate. So then how? So you can find that 3 inputs and then 1 output, and then also you can find the additional line here. So logic and 1. So this is the type of the system error. Just we learn about the type, data type. But you can understand that this is the internal node. So this is the name of an internal node. So, and then you can find that the end3 is here. So, and then this is the module name, and then this is the actually instance name. So we will learn about later. So, and then A, B, C, and 1. So it represents this A is connected to the input of end3A, and then this B is connected to the input of end3B. C is, and then N1 is connected to the output. And then inverter is here, and then N1 is connected to the Y. So N1 is connected to the input of inverter A, and then Y is connected to the Y. So this structural model defines that A, so this is the input of A, B, C, okay, and then so this is the module, and then this is the Y. But inside of this module, we have AND gate, and then this is the N1 internal module, and this is connected to the inverter, and then it's connected to the output Y. So what can you observe? So in the structural modules, we can use multiple sub-modules. So internal modules. So it's a simpler modules. So inside of this NAND3 module, so NAND3, so we define input and output. And so we can also define the internal node here. So what I did is I allocated another modules like end3 and inverter here. So I allocate the other modules here, and I connected the input and output ports, right? So N1 is here, and then it's connected to build the larger module like NAND3 gate. This is the structural model. So in the structural modules, so we can connect the sub modules, and then to build the larger module. So like this, in the structural models, we can also it's called the instance. We can just allocate or we can just instance the multiple submodules and then connect the input and output of these submodules using internal nodes. It's wire, right? That's like this. So this is the structural modules. Okay? So we can define the system behavioral modules like the behavioral model or structural models. Okay? So this is the basic of the system value. System value is the case sensitive, like C. So it means that the uppercase characters is different from the lowercase characters, right? The case sensitive. This example, this is different from the uppercase R we said. Okay, so you need to be cautious of this property of the system value. It's a case sensitive. So, and then no names that start with numbers. So the names, the data types or the module names need to start with the alphabet or characters, right? Not numbers. Okay. So this is not possible. 2 mux. So mux 2 is okay, but 2 mux is not okay. And then white space is white space just ignored. Then you can use the commands like the single line command and the multi-line commands. So it's the same to the C, right? So this is the some system value basic. Okay, so I will stop here and then any questions? Thank you for listening and see you in the next lecture. 감사합니다.